Hi everyone, welcome to this week's CERIAS security seminar. This week I'm very happy to introduce to you Professor Joe Lee of University of California, Irvine. So Joe leads the data-driven security and privacy lab and has done a lot of interesting research in different aspects on internet security, organizational network security, privacy enhancement techniques. He is recipient of numerous awards, including NSF Career Award, Amazon Research Award, Microsoft Award, and a lot of other prizes. So I'm not going to read all of them. So Joe, if you want to get started.
All right. Thank you for introduction and thank you for inviting me for the Purdue series talks. I'm really happy to be here. I watch a lot of the recording there, lots of interesting stuff, and I'm happy to contribute to this series. So today I want to talk about like one branch of my research, which is about applying graph learning for the cyber attack detection. So it's gonna take about 45 minutes and yeah, in the meantime, if you have any questions, you can just let me know, or I can just save the QA in the end. I guess audience are familiar with the basic context. I just want to quickly go over like why this is a big problem. I think currently in the today's cyber attack landscapes, my feeling is lots of attacks become more and more complicated, and they usually take multiple steps. You can see lots of details of those threat actors in lots of news reports, articles. Typically, they take the lots of preparation stages to set up their initial access to vulnerable machines in your organization. And then they try to run through the exploitations and escalate their privilege, like from the normal users to the root users, and then continue to move from their targets from vulnerable machines to the servers and finally to their targeted servers, exfiltrate the sensitive data and send it back to the attackers. So lots of steps, lots of connections. And then to detect such kind of sophisticated cyber attacks, the traditional approach, and actually I summarize those approaches as table-based security analytics. So the whole idea is to collect the data like logs from the end hosts, like system logs like Windows ETW and Linux ODD, and this operating system logs. They also can get the logs from network appliances like intrusion detection systems, and then they represent the data as a table, just like what I show here. So you have many rows, many columns, and then you apply either heuristic-based approach, rule-based matching, or the machine learning-based approach. But the outcome would be alerts. So the alerts can be on the row level or on the cell level. Um, but I mean, this whole business has been going there for quite some time, like, and then it's become billion-dollar markets. But still, the solutions has quite a few critical problems from my perspective. They often generate a high number of alerts. Based on my experiences in my previous employer, which is called RSA Security. I mean, we talk to customers, and then sometimes they say it's not only from our products, but from other people's products. I mean, the number of alerts are a lot. And then whenever we present them alerts, it's more like individual events. So we do not really draw the connection between the alerts. So we don't really tell the story. Nice story like the articles we see there about their attack strategy, their connection, their steps. We don't have those information if we apply table-based approach. So at some point, my feeling when talking to the people working on the field is there are just so many alerts from so many different security products, and then the human are burned out and they don't want to spend too much time in looking those alerts generated from the machine solutions. So there has been some progress and I think motivation and also initiation from the academic side, which I call as a graph-based security analytics. So the whole idea at a very high level is to, instead of representing the data as table, we represent the data as a graph. So we construct a network log graph and a host log graph, or both cases. And then we apply the graph learning algorithms like the ones without any training. So we can apply something like backtracking, reverse search, belief provocations, and then we start from something we know as malicious and detect the other abnormal instances as nodes or edges. And then we can also apply learning-based approaches. And actually, this direction has gained a lot of momentum in the recent few years because lots of newer machine learning models for graph has been developed, like graph neural networks, GNN, graph2vec, graph-sage, and lots of academic works I see recently is to adapt those machine learning models to the data we have. A nice thing with the graph-based approach is we can create alerts with different granularity, and we can create connections of the alerts. So we can do the node level classification, edge level, subgraph level, and even we can do something like data provenance, which I want to talk a little bit more later. So there has been some survey of this area in the academic side. There was a survey paper that was done 2 years ago. And what they show is they count papers published at the top tier conferences. And already over 100 papers has been published since 2003. And there's another paper, they surveyed the industry companies, like 10 companies, and 4 of them has been using this kind of solutions. So there has been some momentum in both sides. So I want to give a few examples regarding the graph we typically deal with, and then the architecture we have so far. There are frameworks in processing those kind of data. So for the first graph, we can construct from the host logs. So we assume there has been some endpoint monitors, EDR products, collect the data, and then each node can be a process, can be a file, can be a sockets, and then we try to, draw their connection to edges about their operations, API calls. So in this example, the red boxes, like the PowerShell, can be something we know that's malicious. They run some malicious commands, and then we can trace back from the PowerShell to the other boxes or nodes that lead to the execution of PowerShell. And then later we figure out, okay, maybe this is because a user downloaded these malicious documents and then runs drive-by download and then run these PowerShell commands. So you can see with the graph, we have more contextual information about why these bad things really happen. We can also do so for the network logs. So in that cases, we can have the host, users, and the domain names as the nodes, and then edges as network communications like authentications, net flows, DNS queries, but we can have a good graph with lots of features on it. And in this example, it is about a simulated attack campaign from DARPA OPTC datasets. And then there have some really interesting graph pattern. So for example, the attackers runs these lateral movement techniques to go from one host to another. You can see lots of edges connect with each other sequentially in a short period of time. And this is kind of an indication we have for the lateral movements, and you can actually, get those indications from the graph perspective. We can also find there the server, once it was compromised, it tries to brute forcing the nearby hosts it connects to. So you may see a large out degree from this edge in a small period of time. And again, this was an interesting graph pattern that can be learned from graph learning algorithms. Okay, so the research has been going on there for a while. The major body of the research actually focusing on a few challenges, and then the challenges are still there based on my my research and my discussion with my industrial friends, and then I want to point them out, and later I want to highlight what kind of challenges are partially addressed in my works. So the major issue regarding the GSA, the graph-based security analytics, is the scalability challenge. The data sets we are dealing with usually are of really, really large volume. The endpoints creates a lot of data. Network appliances creates a lot of data. And the more those kind of products you run, and then the more logs you got, and we don't miss anything. So there will be logging overhead on the clients, a large data volume, and you need to deal with different log sources, and then the data has to be continuously analyzed and processed. And besides, I think the accuracy issue is an even bigger deal from my perspective, especially you are dealing with the real world, large-scale data sets. There are 2 data sets I've been playing with for a while. Both of them are network data sets, one coming from DARPA, one coming from the Los Alamos National Labs, I call them LANR data sets. So if you look at the events, number of events they have, the ratios between the whole number of events with malicious number of events are really large, and it can be more than 4,000 and even more than 1 million times. So this is hugely imbalanced data sets, and if you want to achieve high detection accuracy, it's not easy. And finally, since we are building security products, we are dealing with attackers. And then attackers has incentive to support our system. So they can either compromise the integrity of the log collection, or they can just tamper our graph learning algorithms. My perspective in this area is this is actually a good thing. If we see the research challenges, we can do more research. So that's the reason actually I spend lots of time on this line of works, and I have quite a few people in my labs working on that. Okay, so before I dive into the details of my works, I want to give a high-level overview of the works that has been done in this space by layers. There are stacks, and then I want to talk about where my work was aligned to. So for those 100 papers, and actually this survey paper, which was published in Secret and Privacy last year, position them into 5 different layers. The first layer is capture layer. So the works are about optimizing the data collection algorithm, mechanism, and reduce the collection overhead. And on top of it, there has been some systems to reduce the data that's gonna later be analyzed by the detection algorithm. So why this is possible? Because most of the time the logs are just benign, like nothing relevant to attack. So if we can easily filter out those irrelevant logs, we will have a much smaller data to work with, and then we can make machine learning algorithm or heuristic-based algorithm have much better results. So there has been some works over there. And after that, people build infrastructures to support the analysts, humans. For example, they build a new domain-specific language to help the users to run arbitrary queries in a way more expressive than the circle language. There has been some works there. And then there are also works in optimizing the storage support to make the analysis faster. So, and after all those steps, we can start to run the detection. So we can do the heuristic-based detection and anomaly-based detection. Then we have a bunch of alerts. There are some papers to the alerts correlation, alerts ranking, and the log integration. So if you think this whole research is about machine learning, it's actually the machine learning, the core machine learning part is this small piece. I feel the nice thing about this research is it's more like system work. You need to build a system. It's not only about machine learning. There has been lots of things you need to consider from application perspective, which is really interesting to me. So I want to talk about my 3 works that was aligned in this space. I may talk about one, two, and then given the time, if I have more time, I will talk about the third work. And I want to leave some time to talk about some of the research opportunities that I think were some publication papers, and finally some thoughts of the whole area. Okay. So the 3 works I'll talk about actually the first 2 are aligned in the place of anomaly-based detection. So we apply the graph learning algorithm. It's training based to detect the attacks based on their abnormal score. And then I also have another work which was published like 3 years ago that tries to compress the data to enable more storage efficient analysis. So these are my 3 works. So before I will dive into more details regarding our systems, I want to talk about the workflow of this anomaly-based GSA, like how the graph learning algorithms are plugged in. So whenever we have the logs as host network logs, we construct the graphs. Okay. And then if you do the graph learning based approach, typically people will follow the graph autoencoder system, and then they will choose a graph encoder. And the normal choice is graph convolutional neural nets. So basically treat the graph as a large genesis matrix and then run through a few neural layers and then identify and build up something. So the output are typically node embeddings. So each node is gonna have a high dimensional, numerical vectors, which try to contain information of the node itself and its neighborhoods, which can be 1 hop and 2 hop and multiple hops. Okay, and after that, we run the node embeddings through the decoders, which can be the simple inner products or multi-layer perceptron, like those neural network decoder. And then we can recover agency matrix with probabilities of each edge. And well, we can recover the probabilities for the node embeddings, but we are trying to reconstruct the data from the decoder. And then we can apply the threshold on the probabilities, and then we can tell whether an edge, a node, or the subgraphs are abnormal or not. And then we give the results to human. So this is the common workflow. And actually in the paper I'm going to talk about, we survey the prior works and then we identify like 3 issues we think should be addressed from this point. First, we found quite a few papers building the static graphs on the logs. So they may have just one graph for the whole year of data, which we think is not really good at granularity and makes investigation harder, right? And then, I mean, the papers we see before us will just use a single log source from the data, but typically in the enterprise setting, they have many different security products. So you're gonna have different log sources, and then it's better to use actually more data to have better detection algorithm, but you will need to design something a little bit different from the traditional graph learning, framework. And then finally, most of papers, they train their models in a target to get a high AUC. But in imbalanced data sets, we found this is not really the right metrics we should pursue. It's actually better if you try to train a model to get the high precision. And I'm going to explain this issue a little bit later. So the paper I want to talk about was actually published in this year's Security and Privacy, and the work was led by my student Jason, and he made the presentation at the conferences. So the paper system we built is called Argus, so it's short for the attack-aware, graph-based, and supervised security analytics. The goal is to detect the malicious edges on the sequence of snapshots. So we are not building a static graph. We are building a temporal graphs. And then we test our system on large-scale log datasets, network log datasets, and we are able to achieve high precision. For example, in one datasets we run, which is called Lambda Cyber 1, we are able to achieve 7 times better average precision than the previous SOTA system. So I mean, you may find this interesting because how would it be possible? Like you have 7 times better average precision. The reason is the baseline average precision of the prior systems were not really high, less than 10%. So we're able to actually get a much higher average precision, but still we are far from the optimal results. I mean, this data set is really challenging, I would say. And the system is highly scalable. It takes less than 20 minutes to actually train our models on commercial NVIDIA GPU. And then we are able to process 200 million logs in this scale. And we also test some of the attacks against our system is robust in some perspective. So I want to actually select a few components to spend more time, and then the other details are in my paper if you want to learn more, and please check our paper. So firstly, regarding the graph modeling, instead of using a single graph, we can't cluster the logs into smaller snapshots. So we order the logs by their timestamps, and we select a fixed time window, like 1 hour or 30 minutes, and then we create many smaller graphs. And on each temporal snapshots, we throw them into a graph convolutional neural nets, which is an encoder. So because the graph is smaller, so we are able to achieve higher scalability. And then we're gonna have a bunch of node embeddings for each snapshots. And then actually with this modeling, we are able to capture the temporal patterns with the other neural nets, the recurrent neural nets, RNN here. So with RNN, we can throw in the sequence of node embeddings for different snapshots and update them, okay, based on the optimizations to get a better, representation regarding their temporal spatial patterns. So this is a nice thing of, I think, of our system. And finally, we can decode our snapshots and then to run the anomaly detection algorithms. Okay, so regarding the encoders, one thing we did is to include edge features. And you may think, okay, this is kind of trivial thing to do, but it turns out not so straightforward, from the existing graph neural networks. We think this is important because, the logs can come from multiple different sources in a real setting. For example, You can have the appliances collecting the net flows, appliances collecting the authentication logs. Server can do that. And these logs can naturally correlate because they share the same source and destinations like the IP addresses, users, so they can be really correlated. But if you try to run them through the standard GCN encoder, I mean, you try to plug in those logs fields into the edge features, they are not easy, they are not directly handled because if you look at the GCN function on the right, so the input is the node features X, okay, and the adjacency matrix. And typically, the adjacency matrix is only about their connections between the edges. They don't encode the content information of the edge features. So we need something else than GCN. So what we do is to firstly run this edge feature engineering procedure, and divide the feature into different types, like categorical features and numerical features, and we try to model the categorical features by their item frequency. So by the end of the day, we're able to get some numerical values from the categorical features, like for example, we can model the protocols each network flow goes through and the user, the type of the connections. So we are able to convert those things into the numerical features by counting item frequency. And then we normalize the categorical features and numerical features into this feature vector. So we're going to have a bunch of numerical values. Then the next thing is how are we able to merge those features into the GCN? So we found there was a work called a message passing neural nets MPN encoder that can be combined with GCN encoder. So what we do is to, start from node features like the X, which from the source, and then looking for the edges that starting from these nodes. And then because each edge has been encoded with one edge feature or the edge feature vector, and then we can summarize those edge features with another neural net, like multi-layer perceptron. So we're able to kind of keep adding those numerical vectors together and into its finally to its origin node features. And then in the end, we're able to merge edge features into node features. And then we can send these results into the conventional GCN and let things to keep running and finally get our results. And the other things we tried actually to optimize the existing work is instead of training for the accuracy, we are trying training for the precision. So let me talk a little bit about the differences between accuracy and precision and why this matters to us. So the standard approaches for the training use things like cross entropy loss to maximize the accuracy. But if you look at accuracy equation, it basically treats the true positive, like the malicious events, the same as true negative, the benign events. So this is something I show in the equations on the right. But in my opinion, those two things have different weights and needs different attention because the data set is highly imbalanced. So there can be millions of benign events and one malicious events. So they shouldn't be treated exactly the same. And from analyst perspective, they care more about correctly classifying malicious events rather than correctly classifying benign events. So instead of optimizing for the accuracy, we propose to optimizing for the precision. And we actually adopt this average precision loss into our framework. So the precision can be written in the equations on the right. So you divide the true positives by the sum of the true positive and the false positives. So there is no true negatives or false negatives there. So we put much more efforts or attention into the malicious events. It's better for the imbalanced data sets we have. But the average precision equation we have cannot be directly optimized under the machine learning algorithms. So we adopt the methods from this paper to build an approximation of this average precision equations. And this thing can be, the thing on the bottom can be optimized so we can keep training our systems to achieve better average precision. Okay, so we test our systems on two data sets, and both of them are large-scale data sets. The first is Lander Cyber 1, and then this is a data set with multiple sources of logs, including authentication logs, flow logs, DNS logs, and machine logs. And in the end, we found authentication logs and the flow logs can be used together. And both of them has huge number of events. And then the authors also simulate some red team events but you can see the ratios are really large if you look at the authentication logs and flow logs with red team events. We test our systems and the other baseline methods, including the normal non-graph-based approach and the graph-based approach. And before us, EULA is the one has the best results, but we found its average precision is not really, good enough, and we're able to actually have 7 times better average precision, which is 0.32. But still, you can feel, okay, this is still far from the best situation. I mean, this data set is just so challenging. And we are still working on that. Hopefully, can have even better results. And another thing I want to point out, which I found is really interesting, is if you look at AUC part, the AUC of last 4 systems are all very high, like more than 0.95. But the average precision differences are huge. So we always feel like if you measure the AUC on a secret data sets, that can be misleading. And we really advocate the measurement on average precisions. We think that's going to be more meaningful. Okay, and similar results are also observed in other data sets, which is the DARPA OPTC data sets. So in other cases, we have relatively more balanced distributions. So the baselines are performing better, but still our system is can get the best results, both AP and AUC. Okay. So the next thing I want to talk about is also a system we built to do the anomaly detection. So in this case, this was a paper published in last year's Usenik Security. So we can change our goal a little bit. So instead of detecting the malicious edges, we try to detect the malicious subgraphs. And then we try to identify the indicators of attacks on the subgraph. So the goal is kind of change a little bit. This time we test our system on the host log datasets, but the modeling is similar. And then we're able to achieve really high precisions. The precision is measured on the classification of subgraphs. So we can get the perfect precision record accuracy on this DARPA engagement datasets. And it's highly efficient. And also we test some adversarial attacks. It's robust in those cases. So I want to, for this one, actually, I want to show, again, just select a few components to talk in details. The high-level graph construction part is the same, actually, very similar. So instead of building a static graph, we can cut the graph into multiple small pieces on the temporal dimension. So we have a bunch of snapshots. And we change our encoder from the GCN into the graph2vec encoder, which I'm going to talk about in next slides. And then we have a bunch of snapshots sequences, they're embeddings. And then we apply another RNN called TextRCNN to detect abnormal snapshots. And then we identify their indicators or nodes that we consider as malicious. So this encoder we use is called graph2vec, is something kind of being spared by the NLP domain. So in NLP, we have some model like doc2vec, which is able to convert a document to article into a vector. And that's something people use to measure the similarity between the documentations. And we found the graph2vec can do similar kind of thing, basically measure the similarity between the graphs. So we are willing to use that. So at a high level, the graph2vec just basically take every node and try to build its vocabulary. Okay, we have this naturally in every other languages, but we don't have those in the graph. So the idea of graph2vec is to start from a node, collects data, collects node features, its nearby edges, the edge features, and then combine everything together. They call it a label. So they combine all the labels together and use the labels aggregations to represent each node. And each node is called RSG or rooted subgraphs. So with that, you can actually create a different word for different graph nodes, just like you create an article. And after that, you can run NLP doc2vec on this RSG vocabulary to generate embeddings. Okay, so we can use graph2vec to embed a whole graph into a vector. The previous work, we do the embedding on each node, but this one, we can embed the whole graph. So to training to get a better representation of the graph, the goal will be designed as to maximize the co-occurrence likelihood of snapshots and its RSG. So I show the equations on the right. So high-level idea is to keep doing optimization updating your graph vectors, which starts from a random vector and then keep changing it and changing it until some time these equations has the highest results, or the lowest loss. So you're gonna see it becomes more similar towards its aggregation of its nodes or RSGs. So it's a whole optimization procedure. And we also do something special in our application domain. So we run an actual process to deduplicate certain edges or nodes. So with that, we have smaller graph, and then we can generate the embeddings more efficiently. So after we are able to generate the embeddings for what is snapshots or subgraphs, we want to actually go further. I mean, instead of just sending a bunch of graphs to the human analyst, we want to tell them, okay, on this particular graph, which nodes you should pay more attention. So we really want to detect suspicious nodes. And we found if we use graph-to-vec encoder, this thing can be done easily. So why this is the case? Because actually in the training procedure, we compute the probabilities for the graph. We also compute the probabilities for each node. So we can just compute the differences between the probabilities in the training and testing data sets of the same nodes. And then the higher differences means the node is more suspicious, which means it shouldn't actually appear in the testing stage. And then that's something we should pay more attention to. So and there is actually example for what we can do on this Atlas data sets, and this is something actually produced by the Purdue, which is really nice data sets. So we actually so in this example we have 3 snapshots. We identify the last one is abnormal based on the RNN layer, and then we go further by label the nodes inside it as malicious or not by computing its differences probabilities testing and training. And we tell the top 4 are malicious and 3 of them are true positives based on the ground truth. So we basically run our system and testing our systems on a few public data sets. Stream Spot data sets is the one produced in the lab environments, and they label 600 graphs as benign and attack, and then we are able to achieve like really high precision record accuracy at the graph level on these data sets. We also tested 3 DARPA data sets, the CADIS, ClearScope, and Thea. They all simulate APT attacks on their data. So we also got really good results. We also want to show, I mean, try to deploy our systems in commercial EDR products. We work with the company, and they are willing to deploy our systems on a subset of the, clients they are monitoring. So we run our system on 80,000 endpoints over 100 companies. So they deploy the CDR products, and we have this feature for them to use. We collect around 180 gigabytes of data for 9 days. And we compare our system with Unicorn, which is a previous system to the subgraph classification. And you can see our result was much better. Unicorn, which don't use, based on my understanding, don't apply really, deep learning algorithms to kind of optimizing its representation. But this is what we do with ProGrapher. We keep optimizing the graph representation in a learning-based algorithm, so we are able to kind of fit better in this benign data in terms of their graph patterns. And this is, I think this is one reason why we get much better results in this perspective. Okay. So I think I still have some time. So I'm just gonna go through the last piece of my work in how we do the storage reduction on the data we want to analyze. So this work was published in Usenix Securities 3 years ago. And this time, the analysis we do is about heuristic-based approach. So it's kind of a little bit different from learning-based approach because we don't have any encoders, we don't train any encoders. And we just apply the standard graph learning algorithm, like the backtracking, which essentially a breadth searching. So the whole idea here is to start from some nodes the analyst already know as malicious or suspicious, and then we try to identify this root cause. We also call this research as what this line of research called attack provenance. So here, assuming the PowerShell is, defined as malicious, and the analyst want to understand why the PowerShell gets run in this victim host. So it runs the backtracking, go through from time dimension, basically like just look at its history following its temporal orders and identify the first hop actually leading to the execution of these commands. Just go like one hop and two hop and three hops, and then carve out these subgraphs, and then later apply some tracking policies and identify the Chrome is the initial starting points of downloading these Word documents and further run the PowerShell commands. Okay, so then the Chrome can be the root cause in this case. So even though the algorithm is not too complicated, but if you want to support long-term attack provenance in the enterprise setting, you will have to deal with this problem of the storage issue because you will have to keep a large amount of data to represent its complete history. And actually, the industry collaborator in this work, the NEC Labs, they told me they are only able to sustain 3 months of logs from 100 hosts per day. And because just each day they're gonna deal with 5 TB of data. And if you think about storing those data in the cloud products, and I believe many of the companies nowadays run analysts on the systems on the cloud, not on premise. So you need to rent the cloud spaces for it. And the problem is cloud storage is typically costs you a lot, and then you may really want to reduce storage overhead. So there has been some work to reduce the storage overhead, and they work as reduction layer. For example, prune the logs, do the lossy compressions, but we could argue those approaches has this problem in that they cannot guarantee 100% accurate outcome because you don't really know what kind of benign logs can be later leveraged by the attackers. And then we are thinking about, can we do the lossless compression on the data? We can still satisfy the provenance effectiveness, accuracy, and we can also satisfy the provenance efficiency. So the lossless compression usually will make your analyst query slower, but we found we're able to achieve, get a solution to address that. And our system is called SEAL. So we test our systems on the DARPA and NEC log datasets, and we can achieve really good compression ratio. And we found it's also interesting, like the provenance or the query latencies can be most cases even smaller actually than the data not compressed, uncompressed. So I will likely dive a little bit into details of this system, and then later I'm gonna show some of the thoughts I have. So basically we look at the existing lossless compression tools, standard tools like gzip, LZ4, but we found none of them are good enough for our problem. They either incur really high decompression overhead, or they don't really support the constraints we want to have for the provenance analysis. So we start to look at the other literature, and we found this really beautiful and nice, elegant idea that can support our goal, which is called query-friendly compression, or QFC, based on a paper published 10 years ago. So they define the QFC as a graph that can be compressed in a way they can still be queried efficiently without decompression. We found we cannot really fully support this notation, but if we divide our data into two parts, the graph structure and edge properties, we can treat them differently. So in the end, we found we can run the decompression-free compression on the graph structure, meaning that we can compress the graph and run provenance query to get our result without any decompression stage. And then we can later decompress the edge properties because the number of edges are suspicious are relatively small, so the decompression overhead are also small. So I have an example, but I want to skip in the sake of time. But in the end, we found by applying our systems, we can achieve really good compression ratio on two data sets we have. And we also try to draw the distribution of compression ratio on the 95 hosts of the NEC data sets. And we found most of them, we can achieve more than 50% of compression rate. And also, because our decompression only on a small piece of data, okay, on the edges of the subgraph, and then that part only takes less than 20% of the time. And for the provenance query, usually they need to go through many different hops. of your graphs because we don't really change the graph structure. That part don't really require decompression, so we have no overhead in this part, and so we're able to achieve really good results. I want to use maybe the last maybe 5 minutes to talk about some of the opportunities I see in this space and conclude my talk. So far, there has been really this area has really been, I mean, going well in my opinion. I see more and more papers published this year. I attend the Secret and Privacy, and actually there's a whole session about this research. I think like 10 papers published in the top tier conferences in one session about this problem, which really encouraged me to do more in this space. I think there are a few things we can do better. The first, we can keep finding the newer graph learning algorithms beyond the standard GCN, the graph sage, like TGN is something new, and actually this is something was applied in this year's paper, one of this year's paper in Secret and Privacy. And then we can also think about other ways to construct the graph instead of the static temporal graphs. We can also do the hybrid graphs, the multi-dimensional graphs, just making them more complex to capture more information. And I also feel the different security problems can be converged, even though so far only focus on the log analytics. The graph learning algorithm has been applied to other similar problems like detecting the SIBO attacks, SIBO accounts in the social networks, and detect the malicious redirections on the web graphs. And I believe those different areas share some similar properties, and maybe one can inspire the other. In terms of training, so far the recent works advocate unsupervised learning, so only assuming the benign data available. But we believe we can try to synthesize the malicious samples during the training procedures. And actually, I'm currently exploring how to use large language models to synthesize some of the training samples for to make the training better. In terms of scalabilities, based on my discussion with the other companies so far, there's still a gap between the academic approaches with the data they see at the industry scale. So like Amazon, IBM, and Microsoft, they usually have even more volume of data than the public data sets we see. So we have to make scalability better. Robustness is another interesting factor. So the research, I think, has just started. There are a few papers published. I only found two of them talk about the specific attacks against the GSA, and no defense so far. So as far as I know, maybe there's something has been done recently, but as far as I know, nothing on the defense against adversarial attacks on the GSA. So that may be something interesting to look at. And finally, I think so far the privacy issue has been ignored. Largely, people always assume data can be collected without a barrier and then run a GSA. But that's not the case. If you think about the privacy regulation, you are not really free to move the data from one country to another. So how are we able to deal with this issue with like privacy preserving machine learning techniques? I mean, my group is working on that, and we are hoping to publish in something in the near future. Okay, so I think I only have maybe 3 slides to conclude my talk. So to conclude, so to summarize, is my view of this GIC research. I feel really this is something really promising. I see some really good results, lots of papers, some more attention from academia and industry. Um, I think we can, in terms of accuracy and scalability, most of the papers are about that. Okay. And then, but we still need to prove we can do better if we try to deploy on the industry data sets, which are typically larger and noisier. And robustness is something I think really a big deal, but we definitely need more research into it. Whether we are able to adapt the existing machine learning security and privacy, I mean, system into that, that's an open question to me. And finally, the privacy part, I think we need more work. And we could also consider other deployment settings, different sources of log. For example, if you try to protect your instances on the cloud, AWS, you may not really see the down to the detail host network logs. And some of the logs are really coarse-grained. So how are we able to detect complicated attacks on this kind of data, which I think need more thoughts. And finally, this is not really like technical issue in my perspective. It's just like every time I feel if I develop some academic works, it's really it's always hard to convince the people on the field to use my system, especially it's machine learning. It's really hard to convince people like in the security setting, like machine learning works really well for them. So it's also a challenge. But yeah, I do want to see more collaborations if it's possible. And please let me know or email me if you want to learn more about that. So in addition to this direction, my lab also do research in other directions like internet scale analysis, DNS, machine learning service, security and privacy, IoT, mobile devices. This is the talk only covers this part. And if you want to learn more of my research, you can go to my websites, and I'm also happy to talk to more in other perspective. Okay, so this is my last slide. I want to again thank my sponsors and my lovely lab members. They do most of the work, and I'm getting the credits, which I feel really bad. And finally, I want to show a few pictures of UC Irvine, which I think is really nice place to go to. And if you're nearby, let me know. Okay, that's all my talk. Thanks.
Thanks, Joe, for the talk. I think we have a question in chat. So can you see that? I can also. Uh,
Okay.
yeah,
Mhm.
the question is that not clear why graph2vec is used in ProGrapher instead of GCL.
Okay, let me read the question. So in the second work, you generate the embeddings for the whole graph use graph2vec. Another method which is used for classification graph is GNN. So has any experiments been done on it? So what? Okay. So we didn't try GNN. I'm aware of GNN, but we didn't try that. That's a good thing to think about. We tried the graph2vec. I think the reason is firstly we want to get the embedding for the whole graph. And at that time, I mean, I work with my collaborators, and we found that this graph2vec can generate a graph level embedding. And just like the doc2vec in NLP, we're able to generate the embedding for the whole article. So graph2vec can generate the embedding for the whole graph. So that's the reason we choose it. Um, yeah, but there may be other approaches as you mentioned, and also works. So yeah, I'm happy to talk more if you want to learn whether this can work or not. The second question is, can an idea be given about how you have compressed the graph in a decompressed free way, why the compression was not lossy? Okay, so the compression we do, yeah, actually I skip the details, is so basically, we compress the graph structure and also the edge features like the numerical values, like the categorical values on those edges. So we have different parts. For the, let me see if I can quickly show this one here is to compress the graph. We actually merge the nodes based on their destinations, and we replace the nodes with a table. So in the end, you can think about it, we reduce the number of nodes, okay? And then we have smaller graphs, but with a table, we are able to kind of recover the whole graph after we finish the analysis. So that part is decompression free because we actually, if you run the backtracking, we don't really change the sequences or the steps you do. But for the node features, is losslessly compressed because we use those lossless compression algorithm. I think we use the Hoffman encoding and then delta encoding. So those things make sure you don't lose anything. So later you can decompress without any information loss. Yeah, I hope I understand the issue. Uh, Let me see. I think there are some other maybe chats questions I can see.
There is one question on the top of the chat, if you can
Okay,
see.
okay. Uh, Oh yeah, sorry. I firstly see the QA question and then the chat question. So actually I answered the QA question. But I think I also partially answered the question about the graph2vec. Because yeah, the standard GCN I think is able to directly output the kind of the edge probabilities because it's what it does is a node embedding. So you can get an edge embedding the edge probabilities. But graph2vec is something we can directly get the graph level embedding. And also we do this graph2vec work earlier. So that may be a reason we choose this thing first. And I think later after us, more people are using GCN. So we are also do something on top of that.
Yeah, any more questions from the audience? So, Joe, I will like ask a very generic question. So, I definitely agree that for analytics, graph is a very interesting
Mhm.
tool to analyze. So, if you could like give some more examples on uh, applications of graph neural networks or something like that, I think then students might be more interested in using graph neural networks for different application domains.
Oh, okay. So yeah, I think there's lots of other things you can do with graph neural nets. So that's something I show. I think I talk about a few things here, a few other examples. So I think if actually able to represent the data in the graph, and then there's high chances you're able to apply the graph neural networks. For example, I think I saw papers apply the GNN to detect the social network SIBO accounts. So those are the fake accounts, right? You can register and promoting some misinformation. So assuming you have some data like labeled as benign interactions between people and you train on it to get a GNN model, I think you should be able to get some really good result in predicting which nodes or interactions or edges are misinformation related. I'm sure there are papers about that. And another relevant area I see have huge promises is in the financial applications. I saw actually I do really know people and talk to people. They apply GN to detect financial fraud. If you're able to, I mean, construct the graphs of your financial accounts, their transactions, and lots of those financial activities have their unique patterns. For example, I heard there are people doing money laundering, like they transfer the money from one banking account to another and going back. So you can actually see those circles in those transactions in a shorter period of time, but usually you don't see it in the normal transactions. And this is just one example. There, with GNN, we can actually model more complex graph patterns, and so we can do more detection. So in the end, I think there's a lot of things you can do with the GNN on the other settings, relevant settings.
Okay, yeah. With a follow-up question to that, what do you think about the different attacks that are possible on GNN, like link
Mm,
stealing attacks, those sort of things? What can be
mm,
the
mm.
security and privacy challenges if someone actually wants
Yeah,
to
yeah,
exploit
yeah.
GNN?
Mm, mm. Okay. Mm,
So I think we have one more question. If
mm.
you want to look into that, and we are running out of time as well. But yeah, I think this question
Let me see which one I didn't see
it's
from.
in the Q&A.
Oh, I think I answered the QA question in the beginning.
Yeah, but I think this is a new question that has been asked. So this is from a student called Mirza who says, "Thank you for the interesting talk."
Okay, I see
Yeah,
it. Okay.
I-
Okay, I see it now. Yeah, I think I answered that. So for Argus, since it looks into temporal information from the logs, I wonder how it works for the online detection. It has already seen logs up to the time step t, where it only need to append the nodes and edges for timestamp t plus one, or it will compute the whole graph again for the beginning. That's a nice question. So I think I can break the question into two parts. Firstly, the online detection. What we do is actually we are not really real-time detection like you give me an edge, I directly tell you yes or no, because we need to wait to create the whole snapshots. So usually we need to wait for like 30 minutes, 1 hour to have snapshots, and we start to do the classification. So I think it's between offline and a truly real-time detection. And then regarding prediction of the I mean of the future snapshots. So what we do is because we when we have the data, okay, and we slice it into snapshots. So you can think about snapshots from timestamp number one to maybe t and t plus n, and then we give everything into Rn. And then with RNN, it's able to update every snapshots, embeddings, and also do the prediction using the snapshots before, like before T and after T. Like if you want to classify the T, you can use 1 to T minus 1, T plus 1 to N, something larger than T plus N. So you can use something before and after it to tell whether this T snapshot is malicious or not. This is something actually RN can do. So so in that cases, we don't need to compute the whole graph again. So we just keep adding new snapshots, and then we do the encoding, and we use RNN to kind of keep updating the scores and do the prediction on different snapshots. So I hope I answered the question.
Yeah, I think, yeah, let's thank our speaker. Thank you, Joe, for your time. I think we are at the end of the
Hmm.
presentation for our time. It was really interesting talk. I think everyone learned a lot about graph-based analytics. So
Hmm.
thank you.
Okay, thank you for inviting me. Okay.